Okay, let us start the last morning talk, and Professor Nikonov tell us about rates of crossings on functorial maps.
Thank you. My talk is devoted to picture valued invariance of nodes, and I will present some example of nodes and try to give a universal approach more universal approach to such maps. So we exploit the combinatorial approach to map theory, where we can think about nodes as diagrams, equivalence classes of diagrams, modular sum, so known as reduced. We consider picture valued invariance, that is, we consider two node theory. Node theory is a set of diagrams and moves, a set of moves between them. We can consider different sets of moves, and we will get different node theories. And in general, we have the initial source node theory, which is the usual node theory with right-most moves, and then apply some local moves, which transforms diagrams in some other diagrams. And if the result will be invariant, that is different diagrams which differs by reduced moves give the same result in the destination of theory, we will call it a picture valued invariance. So some examples about such invariance. The most known example maybe is the Kaufman bracket, which is defined for classical nodes. In classical nodes, we consider every crossing and then replace it with two smoothing with coefficients by the Kaufman smoothing rule, and we get a diagram without crossing, and then use one move on that diagram without crossing, which eliminates a simple circle and to replace it with some multiplier delta. Thus, we can reduce all circles in classical case to empty diagram, and we get a polynomial invariant. So this is an example. We start with a classical node theory and use a smoothing rule to get in a node theory of diagrams without crossing with one move, circle reduction. Another example is derive co-brackets. We consider a surface and oriented curves in the surface oriented curve, and then take each crossing, take one crossing, and then consider an oriented smooth at this crossing. We get a two-component link, that is two components, and we enumerate these components and apply this result consistently, consequently to each crossing, and get a sum of diagrams. Each diagrams is obtained by a smoothing at some crossing, and the result will be two-component flat link in a surface, and one can check that the result doesn't depend on the initial curve. So it doesn't depend on homotopy of the initial curve. So in this case, we have a different type of picture valued invariant. We apply the smoothing rule only at one crossing at once, and then take the sum. And besides the reduced move in the destination of theory, there is also a move O0. It is the move where we just, if we have a simple circle, we assume that the whole diagram is zero. So the third example is Goldman brackets. it takes a two-component link with ordered components on a surface, and then by smoothing produces sum of nodes of one component, a flat node on the surface. And the rule here depends on the type of the crossing. There are two types. In the crossing, two components may intersect I and J. And if we have a pure crossing, that is self-intersection of a component, we get a zero. And if components are different, we have +1 or -1, depends on the number of the components. So the result will be a sum of flat nodes in the surface. And here you can note that the rule, the smoothing rule depends on the crossing. For different crossing, we have a different result. And this this factor can be used by Vasily Matrov when he defined the bracket, the parity bracket. He dealt with 3 nodes, so that is virtual nodes up to crossing change and virtualization move. And then in that node, we divide crossings into 2 parts, odd crossing and even crossing. And at each even crossing, we apply the smoothing operation. And the result will be a linear combination of graphs, which we consider up to the second randomized move and virtual randomized and the move which remove the move O0. That is, if we have a trivial circle, then the diagram is 0. So this is an invariant of virtue of flat nodes and of free nodes with the values in linear combination of graphs. And another, here we have the rule of how the crossings should be divided into odd and even. The rule is the following, that the parity of a crossing shouldn't change after applying a randomized move. And the second condition is the sum of the labels of the crossing which take part in a randomized move must be 0. So if the label is element of Z2, we have the definition of the parity. So if we have such a label, then the previous map will define an invariant linear combination of graphs. And another invariant was constructed also by Mantrov. He proposed to when a crossing is even, it doesn't change, and all crossings are turned into virtual. So if the labeling satisfies the condition of parity or some weaker condition of weak parity, the result of applying this parity projection rule to each crossing will be a virtual node which doesn't depend on the initial diagram. It will be another example of a picture evaluating. So we have such examples, and let us try to formulate a general description of this picture evaluating variance. So we'll start with the definition of diagrams and node theories. So we take a surface, complex surface oriented maybe with the boundary, and consider tangle diagrams in this surface that is 4-valent graphs, and also we may have vertices of valency 1 on the boundary, and at each crossing, at each vertex of volume C4, we consider one of the following structures. We may consider classical crossings, positive or negative. We consider flat crossing, virtual crossing, or a simple crossing. So we have a set of diagrams. We consider diagrams up to isotopy in this surface. And then we denote a special type of diagrams, that is diagrams in a disk. In a disk, we can consider a tangle, diagrams with two ends on the boundary, and we assume that the ends on the boundary are enumerated counterclockwise. So such diagrams will be called entangles. So next, we define a move. A move is a pair of two entangles, which tells then we can take the first angle in a diagram and replace it with the second angle, T2. So we have the replacement operation, and this is the result of applying this move M to the diagram. We can also consider not tangles, but linear combinations of tangles of the same type with the same number of ends. And the result will be a linear combination of diagrams. So there are some examples of moves. We can consider different type of smoothing, oriented and unoriented. We can consider crossing change, a quest move, which differs from the second order moves. This is the quest move, and the delta move, which can be considered when the third order move doesn't. Next, there are HN moves by Hoste, Nakanishi, Takayama, and forbidden virtual moves and flanking moves. So there are different moves. And next, if we take a set of moves, we can define a knot theory as such a set up to equivalence of these sets. For example, this move is equivalent. This class move is equivalent to a crossing change. So different sets of moves can give equivalent result. For example, we can consider classical knot theory with a classical ready-must moves virtual knot theory, where we add virtual ready-must moves to classical flat knot theory when we allow to change crossing. And if we add a visualization move, a flanking move, then we get free knot theory. And there are oriented variants of these theories. And now, for example, red wall, a classical knot theory without the first order must move. So below you can see two examples of moves that produce the oriented knot theory, classical knot theory. That is the example from the Pollack's article paper on generating sets for oriented ready-must moves. So these two sets are equivalent, and they are the same knot theory. Given a set of knots, that is knot theory, if we can consider knot theory on a given surface F. In the surface F, we consider a set of diagrams and then apply this move from the set M to these diagrams, and we get three objects. The set of equivalence classes, that is the set of nodes of this knot theory in surface F. The scheme model, it is a linear object, and diagram category, that is a category where diagrams are objects and the morphism moves from M and their formal compositions. And now we can define what is a trait. A trait is a characteristic of a crossing in a diagram which doesn't change after applying a readiness to move. As soon as we can follow the crossing after the third readiness to moves and isotopies, we assume that its a characteristic, its trait doesn't change. So formally, it can be described as follows. If we have a classical node theory, classical type, that is a theory with rising master moves, classical rising master moves, we can assign to each diagram the set of its crossing, and the trait is a map from crossing to some set, theta, such that the corresponding crossing before and after rising master move must have the same value of this trait, the same trait. So this is a characteristic of a crossing which doesn't change. And for example, if we have some move, for example, second right most of where crossing disappear, then we can say nothing about this. There are some particular cases of traits which are all known in the literature. For example, we can define an index. An index that is a trait such that for two crossings which takes part in the second readiness move, their characteristic must ends. If we have a set with involution, we can define a signed index that is a trait such that in second readiness move, these two values must differ by the invalid. An example of signed index is a parity defined earlier here. It is a parity. We have some additional condition about the sum of the values of crossings which take part in the readiness moves, and with parity. So we have some additional condition on the traits. So now let us define among all traits, there is a universal trait which contains the maximum number of information on this characteristic, and for diagrams in a fixed surface, we can describe this characteristic. It appears that the traits follows from the following labels. The first is the component index, the order index, and homotopy index, and the sign of the cross. If we have a link, we can say with numbered component, we can say which component intersected the cross. So this is the number of components which intersect with the component. If we have a long component, a long node, for example, then there are two types of crossing: earlier undercrossing and earlier overcrossing. And we can differ between these two types, and this is another characteristic. And next, the homotopy index is the homotopy type of half of the diagram at cross. It is an element of the fundamental rule. And together, component index, order index, and this homotopy index and the sign of the crossing is the complete characteristic of the crossing when we consider diagrams in a fixed surface. So there are examples of indices and example of traits. So this index, homotopy index, component index, and this order index are indices, and the sign is sign index in the following definition. Okay, so let us define local transformation rule. We consider a diagram category and a set of combination of two tangles over some commutative ring. So a trait with the values in this combination is called local transformation. Then we can consider replacement according to this transformation rule. For each crossing in a diagram, we have the corresponding tangle, two tangle, and okay, we can replace the crossing with this tangle, with these two tangle. We can replace all the crossing, and we have tau of D new diagram, or we can replace only one cross. And then we have two types, two formulas. The first formula is the sum of replacement at one crossing, the sum of all crossing in the diagram, and it is called tau derivation. And another example is when we apply transformation to all crossings simultaneously, and we get a new diagram called tau functorial. So this is a functorial map.
Can you please provide a couple of examples of the derivation and a factorial map?
Derivation are derived co-bracket and Goldman bracket, and factorial maps are Kaufman bracket and parity projection. Now, the examples were at the beginning of that.
Okay.
So, then we get new diagrams, and we say that these formulas define an invariant if the result produced for different diagrams of the same node will give equivalent diagrams with respect to some knot theory M prime. This is a general definition. And now I formulate some sufficient condition for tau derivation, tau functorial maps to be invariant. Let us start with tau derivation. Let us define, let us fix a knot theory that is a set of moves M, and define the set of omega-3 compatible tangles, two tangles. So they should, these are tangles which are so that the following pictures of three tangles are equivalent in the theory M, in the knot theory M. Another definition is that one note, if we have a trait, in diagram, we have four types of loops, and they give four values of a trait. We have a characteristic, some characteristic of process. And we define the annullator, left and right annullator of with respect to knot theory M as tangles which annihilates after left or right quarter. So this some definition, and finally we can formulate the theorem which states that if we have local transformation rule such that each value for positive crossing belongs to omega-3 compatible tangles, if this trait is a signed index with respect to involution shown in the below the slide. And
what is classical like?
Sorry.
What is classical like?
M contains only 3 reduced.
Okay.
And so the third condition, that is invariance under the first reduced move, is that this loop weights of the trait should belongs to the annulators left and right with respect to the new knot theory. In this case, the duration is an invariant. And we can formulate an analogous definition for regular knots. That is for case when the initial knot theory includes only second and third reduced. And in this case, instead of the third condition, we require the omega 1 plus compatibility for positive crosses. You can see the compatibility condition on this slide. And now some examples. For example, we can consider this operation which glue the crossing, and so that is replaced with a singular cross. And the result is a diagram with one single cross. If we consider the reduced move for this single crossing shown below, then we get an invariant. The tau derivation gives an invariant in this case, and this invariant is the Green invariant considered by Ellis and Henry. And another example is we can consider smoothing. These smooth tangles are omega 3 compatible in flat knot theory, and if we add some term compensating, then this the tau derivation for this smoothing rule will give us smooth invariance considered by Henrich and Chang, Gao, and Xu. And in general case, we can define the trait which gives an invariant tau derivation in the following sense. We just take omega 3 compatible tangles and multiply them by some weight, which are indices. And in this case, this local transformation rule will give an invariant tau derivation, and such the transformation of such type we consider the paper by Gil, Ivanov, Bar, and Lisnin, and they also consider the composition of this of the corresponding tau derivations. And now let us pass to functorial maps. We can write down the condition for functorial maps to be locally invariant, and that is we can draw the reduced move and replace the crossing with some tangles, and thus we get some invariance condition for a functorial. And here we define some subset in the set of two tangles or linear combinations of two tangles, and so you can see these tangles. That one, the low one, should be equivalent in the knot theory M, and this gives us some subset of tangles, and we acquire the condition that the values of local transformation rule must belong to these subsets. And this is just a reformulation of invariance under the diamond moves. So we get such type of theorem, and let us consider some examples. The rest of the talk is devoted to examples of invariant functorial maps. Let us start with unary functorial maps. That is, for positive crossing, we choose only one tangle, one value, and for negative crossing, we choose another value. And for example, if we can consider the identity map, and that is for positive crossing, we choose the corresponding tangle of the positive crossing, and for negative, and this trivial example of functorial map, which is identity. If we take the crossing change, and that is tau plus will be the negative crossing, and tau minus will be the positive crossing, then we get a mirror map. The result is the mirror map. And the third trivial example is that we choose for t plus and t minus the virtual crossing. And the result will be a diagram with only virtual crossing. They are trivial diagrams. And now, a more non-trivial example, let us consider oriented smoothly. In this case, we can write down the invariance condition, and we get, in order to we have an invariance, the destination of theorem prime should include moves O1 plus and H2 plus O, and that is a set of moves with circle. And this they are equivalent to oriented set of moves H2 plus. And if we take not theory, and on some surface F, we get the following functorial map. The corresponding scan module will be the one-dimensional homology of the surface, and the image of the map is just the homology class of the diagram. For non-oriented smoothing, we get an analogous result. Here we the destination of theory is set of move with a circle, and here as the image of the functorial map, we have the homology class of the diagram modulo 2 and some number in Z2, which is the rotation number of the diagram. On the surface, you can define a rotation number like you do in the plane, and you must take this rotation number. And next, we can take a smoothing. It gives us the invariance gives us the set of move, and the corresponding functorial map is gives the homology classes model of the diagram. Next, let us consider the Kaufman smoothing rule. We can consider different rules for positive and negative crosses. And so if you write down the invariance condition, you get that some variables depend on others, and finally you get a two-parameter operation. And for example, for classical node, you get this kind of polynomial invariant of an oriented node or oriented link. And it appears that this polynomial coincides with the Jones polynomial after some change of value. Let us next consider binary functorial maps. Here we have a choice between two values for positive crossing and for negative crossing. In this case, if we fix the tangles tau 0 and tau 1, the transformation rule are determined by a two-valued function. So we reduce our trait to a function tau, which may be 0 or 1. Maybe 0 or 1. So we then will look at tau as this function with values in Z2. And now let us consider the following transformation rule. We can smooth at the crossing. We can take the ranges smooth or unranges. And if you consider all possible cases which can appear in a randomized move, you will have the following cases. And now we must consider different cases for tau. For example, if we have an arbitrary trait, then the destination of theory will include all of these local transformations, all these moves. And in this case, we get the saddle move H2. If our trait is an index, that means that we don't have the cases here 0, 1 or 1, 0, and the move, the new theory will be generated by the move H2O. H2O. So we have three possible cases for M prime for the destination of theory, and depending on it, we have the different result for the corresponding functorial map. In the best case, we have the value of the functorial map, the homology class, and some number in Z2, which is the plus of the rotation number of the diagram and the number of even crossing in the diagram. So we have this functorial map give us element in this product of one-dimensional homology and Z2. If we consider choice between arranged smoothing and identity map, we give the following cases, and the invariance leads us to the following different cases for the create. In general case, we have arranged smoothing and arranged saddle operation. That means in general case, the situation is reduced to unary functorial map, because all crossing can be smooth. In these cases, we have several situations, several sets of moves, and which are saddle move and randomized move, and this move of 2 omega infinity, which is pulling to these butterfly diagrams over some arc. And if we consider the corresponding skein modulus and the images of the functorial maps, we will get the homology class of the diagram, rotation number, the number of crossing, we have three numbers, one class and two additional numbers, which may be integer or in Z2 on the root. So we have such a picture, and there are some other examples. I maybe skip them. When we consider Kaufman smoothing, then we have the following configurations, and there are two cases when we get an invariant. The first one was described by Manturov. He required that the trait is a parity, and in this case, the result will be a diagram in knot-theory with moves O delta crossing change, and the second randomized move, which can be described as a regular doodles on the surface. And there is also another one case where we take a weak parity, and the result will be a regular flat diagram on the surface. And if we take the value for the formal variable a such that the square is equal to 1, then we can define this smoothing on flat diagrams, and then we can iterate this functorial map and get new diagrams from some flat diagram on the surface. There are also another example where we can replace crossing with virtual crossing. And in this case, if you write down the configuration, there are three cases. Among them, the non-trivial are a case when the trait is a weak parity. In this case, we get a virtual diagram. This is the parity projection. And now a new example. Consider crossing change operation. That is, we can change the crossing from positive to negative crossing at some crossings, and other crossings will remain the same. In this case, we have three cases. In general case, we have a crossing change move, which makes the situation trivial. When we have an index, besides the randomized move, we have additional delta move. And if we require that under some additional condition, we have only randomized moves. And this is the case when the trait is an order, which means exactly that this situation 0, 1, 0 and 1, 0, 1 will not occur, never. So we can consider this labeling, order labeling, and it appears that if we
excuse me, you wrote tau and then t and then tau. Am I right that it should be tau of C3?
Yes. Okay. And if we consider a diagram in a fixed surface, and then we have a component type, order type, and homotopy type. Homotopy type is a subset, is an element of the fundamental group, and then we can write Hij for the component for the homotopy type of crossings which change. And in this case, we have the following condition: these sets of homotopy types must be invariant under multiplication. So we have some conditions here, and it appears that these conditions correspond to such notion as pre-ordering on a graph. On a group, On a group, we can consider a reflexive, transitive, and complete relation, and we don't have anti-commutativity here, so there can be equivalent elements, and we also are left invariance of this relation, and this relation is equivalent to distinguishing some subset in a group which is closed under multiplication, and such that the union of H and H minus 1 is equal to group. And we can also define a discrete reordering. This is the case when we have at least positive element that is element such that between one the identity, the unit, and this element there is no other element strictly between them with respect to the period. And we can formulate a proposition so such that an order on node diagrams on the surface F is equivalent to some preorder on the fundamental group where the homotopy class of the node is equivalent to 1, or another possibility that the period is discrete and the inverse to the homotopy type, homotopy class of the node is at least positive value. So in this case, we have such node, and that is some rule to switch crossing of diagrams so that the result will be an invariant diagrams of the same node. And an example of such an ordering is the following. We can consider a parity with coefficient in Z, and then product of parity with the sign of the crossing, and this product will be an order. That is when this product is non-negative element, we don't switch crossing. If it is negative, we switch it. So we have, if we have such a parity, then we have such a functorial map with switching of the crossing. And the last example is the lifting. Lifting, if we have a node diagram, we can forget about crossing and overcrossing, get a flat diagram. And let us consider the inverse map. An inverse map tries to lift, replace the flat crossing with positive or negative crossing. When we try to do it in classical case, or for classical node, we will fail. For example, if we consider this trivial diagram, we can make 3 loops. 2 of them loops will have the same sign. And if we eliminate the rest, we'll get such a diagram with 2 loops of the same sign. And we cannot eliminate these 2 loops with a second randomized move, like we can do in flat case. So there is no functorial map in classical case. On the other hand, if we have a lone node, for a lone node, we always can lift flat diagrams to classical diagrams. And let us consider this lifting map. We have 2 choices, positive crossing and negative crossing. And we can write the corresponding restriction on a trait for it to be a functorial map into classical node theory. That means the trait must be a flat order. A flat order. And if we consider node in a fixed surface and consider the subset of crossings which will be positive and negative. We have some restriction on this subset like this. These two restrictions was in the previous case, and we have a new restriction, and then it means that the corresponding order must be a discrete order, and the inverse homotopy class to the node must be a least positive element, and the inverse is also true. If we have such an order, we can define such a functorial map, and the last corollary, some sufficient condition when a node can be lifted and when it cannot be lifted. If the homotopy class of a node is not primitive, it cannot be lifted because there is no such an order. Another case, if the homology class is primitive, then we have such order, and the diagram of nodes can be lifted. And the last example, we can do this for flat nodes, so that is for nodes up to stabilization. And in this example, I miss the part, and there are two lifting corresponding to first and the second crossing, and the result will be a mirror node to the node 3.4 from the game table. That's all. Thank you.
Some questions?
I have several questions, may I?
Yes.
Okay, so first of all, do you have any new invariants of classical nodes?
No, because for classical nodes, the traits are all constant.
Okay, next, so there is a beautiful theorem of quantum enhancements due to Sam Nelson, which we were developing later by making it agree with parity brackets and so on. I mean, assume we have some coloring. Will it be a classical like or a classical type theory? Can we introduce any sorts of parities, indices, or whatever things you defined if we have colored knots, if we color knots by say quandles or some quandle enhancements?
Yes, if we have covering on the nodes and fixed covering, we can consider the corresponding diagram sets and moves from them, and then apply the same machinery to describe.
Yeah, and do we have any concrete example? I mean, so that we by using that we can distinguish between some two knots, classical knots or colored classical knots, which were not distinguished before.
I haven't considered colored nodes, so I have no examples.
Okay, so you were talking about generalizations of the Kaufman bracket, right? So
Yes.
you were looking at generalizations. Do you have any way of extending the Kaufman bracket? Any way of extending the Kaufman bracket for which uses orientations of crossings, right numbers of crossings? Again, I'm asking about classical nodes. For virtuals, we know quite a lot.
Mm-hmm.
Do we have any things like that? Do we have any enhancements of the Kaufman bracket for classical nodes if we take into account the right number?
The example I get by this formula, this formula also can be applied to classical nodes, but it doesn't extent of Kaufman bracket and John's polynomial, because after some variable change we get the John's polynomial.
Standard. Okay. Okay. Two more questions. So, we heavily rely upon planar projections, so that we do, well, planar or surface, whatever, or two-dimensional projection. So can we somehow do any axiomatics of the same time if we are in R3? And for example, if we do crossing switching in R3, for example, assume we have a knot and we want to do some crossing switch. It needn't be in a neighborhood of a plane, right? So a crossing switch can happen somewhere in R3. Can we axiomatize any well, parities, indices, or operations and traits and whatever, if we do everything not in planar projections, but directly in R3 and maybe inside some manifolds?
Maybe.
Yeah, and
Vasily,
Yes.
I'm very sorry, we have no time for continuation, so please discuss it privately. Or let us thank the speaker again.